All right, next we're trying to multiply our binomials as we've been practicing, but they're hoping that when you do these, notice these are the same pair of factors, same pair of factors, same pair of factors, same pair of factors, that they're hoping that you notice a pattern for something called perfect squares when we're multiplying. And so as I'm doing these, we're looking for a rule that we can say for all perfect squares, and maybe it'll save us some time down the line. So here I'm going to go first times first, outer times outer, inner times inner, last times last. Combine the middle term and get x squared plus 10x plus 25. First times first, outer times outer, inner times inner, last times last. Combine that middle term. And I notice it's a 21 and a 21, which makes 42. Now this one is written as 9x plus 1 squared. It's like saying 9x plus 1 twice. Stretch it out. 9x times 9x, 9x times 1, 9x times 1 again, 1 times 1. And this time the inside is adding 9x and 9x again. So 9 plus 9 is 18, plus 1. And finally, that same thing happens on this last one, where it's like saying 4x plus 11 is happening 2 times. So now we multiply. 4 times 4 is 16x times x. 4x times 11 would be 44x. 4x times 11 again. Are you starting to notice the pattern of what keeps happening with these perfect squares? Did you notice that the middle term keeps being the same thing? So writing a rule for the coefficient b of the x term, the middle term, when multiplying and simpling a perfect square. So we notice, I'm just going to put down a couple things. We square the first term and square the last term. That means multiplying it by itself. But to get the b middle term, we double the product of a times q. So where is this a and q coming from that I'm talking about? Right here. So for example, if it was a 3 and a 7, 3 times 7 was 21, 21 and 21 made 42. If it was a 9 and a 1, 9 times 1 is 9, 9 plus 9 is 18. We're taking the product of that a and that q, and then we're doubling it each time. So the way we would write that little formula is 2 times the product of a times q. We double the middle term. All right. For the next one, we're just completing the square and then writing the product of two factors, the factored form. So here, the b work off to the side. So the little formula is half of the middle term squared. So the b work off to the side here is 8 over 2 is 4 squared. 4 squared is just 16. And then the factors are the x plus 4 squared factors. Likewise over here, we do half of 10 is 5. 5 squared, you got it, that's 25, and that's the x plus 5 squared factors. So where does this factored form come from? It comes from taking half of the middle term or the square root of the end term, whichever way you want to think about it. All right, pause the video, try the last ones. Okay, now the next ones, we're going backwards of the steps we just did. If we cut it in half and then squared it, what would be the opposite of that? We would square root it and then double it. Does that make sense? I'm doing the exact opposite because this time, instead of going from the B to the C term, I'm going from the C to the B term. So let's go try a couple. So if I take 16 and square root it, I get 4, and then I double it. 4 twice would be 8. And then it wants our product of two factors again. It's just the x plus 4 squared factors. So do you see how we did that? We took the n term, square rooted it, and then we doubled it. Okay, let's go try it again on number 19. We take the n term and square root it, and then we double that. And then the product of two factors is that square root value. All right, pause this and try a couple on your own. What is the square root of 625? You got it, it's 25. 25 doubled is 50. Square root of 225 is 15. 15 doubled is 30. Square root of 49 is 7. 7 doubled is, and then that's the x plus 7 squared factors. Square root of 169 is 13. 13 doubled, and that's the x plus 13 squared factors. Now, 25 fourths, square root of 25 over square root of 4 is a 5 halves factor. And then to double 5 halves, 2 times 5 halves is just 5. All right, pause the video, try the last two weird fractions. Square root of 9, square root of 4 is 3 halves. Double that 3 halves is just 3. Square root of 49, square root of 4, 7 halves. And then double the 7 halves is just 7. All right, now they're again going over a Math 1 horizontal and vertical line concept. So remember how we've been writing axis of symmetry or lines of symmetry, and the equations have been an x equal number? Well, lines of symmetry are vertical lines like this. So picture a line x equals 9.5, kind of going like this, up and down on the x-axis. And then picture this one over here, going down somewhere over here, x equals negative 8.2. Well, for an x equals vertical line, it's asking you to find the intercepts of the graph of each equation. Well, there is no y-intercept for each of these because it never touches the y because it's a vertical line. But of course it has an x-intercept because it's an x equals line. My x-intercept goes through 9.50 and my x-intercept goes through negative 8.2, comma 0. So when it's an x equals line, it has an x-intercept but not a y. Well, vice versa, that's what happens on these other two, which are y equals lines. Picture that you've got a graph of y equals 112, something like that. And picture that you've got a graph of y equals negative 4.5, something like that. Well, its x-intercept is none. It never goes through the x-axis. But its y-intercept is, of course, the y value that was given. It's the only place it goes through the y-axis. And that's it. So it's just kind of like a conceptual understanding of horizontal and vertical lines, remembering when it's an x equals vertical line, it only touches the x. When it's a y equals horizontal line, it only touches the y.